So today topic is mathematical reasoning. It's a propositional calculus, part of a propositional calculus. And you know that logic is the basis of all mathematical reasoning. It provides rules and techniques for determining whether a given argument is valid. Logic has practical applications to the design of computing machines. It is directly involved in computer programming and used to verify the correctness of the programs. So that is the important things about logic and propositional calculus. So let's start. Now suppose I'm starting with some proposition or statements. Suppose if I say Kolkata is the capital of Maharashtra, and another one, an elephant weighs more than a human being. Now when we read these sentences, we immediately decide that the first sentence is false and the second is correct. There is no confusion regarding this. In mathematics, such sentences are called statements. Statements. So, a declarative sentence which is either true or false but not both is called proposition or statement actually. So, what is a proposition or statement? Another thing I want to give you, another example I want to give you. Consider the sentence, Germans are the most intelligent people in Europe. Some people may think it is true, while others may disagree. Regarding this sentence, we cannot say whether it is always true or false. That means this sentence is ambiguous. Such a sentence is not acceptable as a statement in mathematics. Okay? So, a sentence is called the mathematical acceptable statement if it is either true or false, but not both. So naturally, a declarative sentence which is either true or false but not both is called a proposition or statement. That is the main idea of the statement or proposition. So if we define again, once again, if we want to define a declarative sentence which is either true or false but not both is called a proposition or statement. Proposition is denoted by the symbol P, Q, R, etc. Okay, these are the symbols we were going to use. Now suppose I will give you some ideas. 7 is less than 5. Some examples. Yeah, it is true. So it is a declarative sentence. It is a proposition or statement. Every set is a finite set. It is false. Every set cannot be finite. It can be infinite. So it is a statement. The sun is a star. True. It is a statement. A plus B equal to 3. It is not always true. It is not a proposition because it is not true if A equal to 1. If you suppose A equal to 1 and B equal to 4, so it is not true, and it is false. It is not false if you take A equal to 1.5 and B equal to 1.5. So it is not false for this value and it is not true for this value. So it is not a statement. Okay. And who are you? Next. Here P is not a proposition because this is neither true nor false. It is an interrogative sentence. So these are some examples where you can say this is a statement or not. Now I will talk about negation of a statement. Negation, it's a negative. The denial of a statement is called the negation of the statement. Let us consider the statement, every natural number is an integer. The negation of the statement is, you can write in three ways. There exist natural numbers which is not an integer, or you can say at least one natural number is not an integer, or some natural numbers are not integers. So you can write, you can explain in different ways the negation. So what is the definition? If P is a statement, then the negation of P is also a statement and is denoted by the symbol negation P. This symbol negation P, and read as not P. This is read as not P. Next, I will explain compound statement. Many mathematical statements are obtained by combining one or more statements using some connecting words like and, or, etc. Consider the following statement. So we are usually using these sentences in combined form using and, or, etc. Suppose if I say a statement, Noman is sincere and intelligent. The given statement is actually made up of two smaller statements. Noman is sincere and Noman is intelligent. So these are the sentences that combined in using the and. So these are called compound sentences or compound statements. A compound statement is a statement which is made up of two or more statements. In this case each statement is called component statement. Component of that statement, compound statement. So this is the definition of compound statement. Now let us have some examples of compound sentences or statements. Find the compound statements of the following compound statements, component statements. You have to find out the component statements from these compound statements. Suppose the first one is the sky is blue and the grass is green. So and number two, it is raining and it is cold. So the first one is sky is blue is one of the component statement. The grass is green, another component statement. So you are combining with the operator and. It is raining and it is cold. So it is raining is one of the component statement, and it is cold is another component statement. So P is this one, it is raining, and Q is it is cold. So you are using and to get that. So and is a connective compound statement. Next is all rational numbers are real and all real numbers are complex. So you are connecting two component statements. One is all rational numbers are real, all real numbers are complex. These are the component statements, and you are using again and for that connecting. So this is the compound statement. By and operator you are connecting. Next is 0 is a positive number or a negative number. So you are connecting two component statements. One is 0 is a positive number, and another component statement is 0 is a negative number. So you are connecting 0 is a or statements, because it cannot be both. So 0 is a positive number or a negative number. Okay, this is how you can do the compound statements. Component statements you can break into component statements, or you can join the component statements to form the compound statements. Next, I will talk about truth value of a proposition. That is very important, because we will form a table, we will form several things, several statements and their truth values. So what is the truth value of a proposition? The truth or falsity of a proposition is called the truth value of the proposition. So a proposition may be take two truth values. It will take two truth values. True, which is denoted by T or 1, false, which is denoted by F or 0. Okay, so let us suppose P is a statement 4 plus 5 equal to 10. So P is a proposition which is false. Obviously 4 5 plus 5 cannot be 10. So P takes the truth value F or 0. That is how you can put the values to the statements. Okay, this type of mapping is called truth value. You are putting some values to the statements. Next, number 2, every action has an equal and opposite reaction. You know that the third law of Newton's. So this is true. So Q is a proposition which is true. So Q takes the truth value T or 1. Okay. Next, what is the truth table? The table which displays all the truth values assumed by the proposition is known as the truth table. So truth table will be like this. You have some propositions. You have some proposition P and Q, suppose two propositions. So P can be true, true, false, false. So if you combine, So Q, true, false, all the combinations are there, true, false. So like is what you want here, that will display in these columns. Okay, what is the operations you are doing. So this type of tables are called truth table. So for truth table, we need some logical connectives or operations or statements. So this is the most important part of logic. Operations, you have to understand the operations or statements. So propositions or statements may be modified or combined in various ways to form new propositions or statements. Different types of connectives or operations are used for this purpose. So suppose first one is conjunction. If P and Q are two propositions, then the proposition P and Q, P and Q is called the conjunction of P and Q. So conjunction is a connective and it will denote P and Q and read as P and Q, and it is denoted by P, this type of symbol. This is cap, P cap Q, P hat sometimes, and this is read as P and Q. So this operation is P and Q. Suppose it is raining. If I talk about the statement, P is a statement, it is raining. Q is a statement, it is hot. So what is your P and Q or P hat Q? It is raining and hot. So this is the conjunction. So you are using conjunction to form the compound statement, and its components are P and Q. So what is the truth table? Let's go for the truth table. So as I explained, P and Q are the two statements and you want to connect them by the operation conjunction. So this is the truth table for conjunction. So P is true, true, true. You write this statement, truth values, true, true, false, false, true, false, true, false alternately. And P and Q, first one will be true because P and Q both true. So first row says that if P is true, Q is true, then P and Q is true. Second row, P is true, Q is false. So the P and Q is false. The second row says P is true, Q is false, and P and Q is false. Third row says P is false, Q is true, and so naturally P and Q is false. And third, last row says P is false, Q is false, and P and Q is false. So P and Q is true if and only if P and Q both are true. Okay, otherwise it will be false. In all the cases it will be false. So this is the table, and you have to understand the truth table for conjunction. So this is the truth table for conjunction. Next, connective operations, connectives or operations or statements is or. P and Q are two propositions, then the proposition P or Q or both, P or Q or both is called the disjunction of P and Q. It's called the disjunction. Previous one is a conjunction, this is disjunction, and this is denoted by this symbol P or Q. This is V. This is V shape. This is sometimes called V. So and read as P or Q. Suppose you have a statement, component statements are P, two lines intersect at a point, and Q is a statement, two lines are parallel. Okay, then P or Q, two lines intersect at a point or they are parallel. Okay, so two lines intersect at a point and Q, two lines are parallel. So how will you connect them? Two lines intersect at a point or they are parallel. That is your P or Q. Okay, so next is truth table for disjunction. You see, first row says if P is true, Q is true, then P or Q is true. Correct. If one of them is true, then it will be true. And second row says if P is true, Q is false, then P or Q is true. So it's quite natural. If one of them is true, then your final value, that is P or Q, should be true. So P is false, Q is true. So P or Q is true. That is the third row says. And the last one is if both are false, then P or Q is false. If P is false, Q is false, P or Q is false. So this is the truth table for disjunction. Truth table for negation is very easy because you have P as a statement. If P takes the truth value, negation P will be false. If P takes the false value, negation P will be true. Implication, that is the most important of all the connectives. Implication. If P and Q be two propositions, then the proposition if P then Q is called implication, and it is denoted by P arrow Q. It's an arrow or a double arrow. This will be read as P implies Q. Okay, P implies Q. If P then Q. So suppose P is a statement Rahul works hard, and Q is a statement Rahul comes first in exam. So how will you do the connection? So P implies Q. If Rahul works hard, he comes first in exam. That is the way. Okay, so that was the implication. So you have to identify the implication, you have to understand the implication. Rahul works hard and Rahul comes first in exam. These are the two component statements, and how will you connect them? P implies Q. If Rahul works hard, he comes first in exam. That is the implication. So let us see the truth table. This is very important truth table. So first row says if P is true, Q is true, then P implies Q is also true. Correct. If P is true but Q is false, then statement is P implies Q is false. It takes the truth value false. This is important because it is false if and only if Q is false. And third row says, I will explain with an example. This is very good, very important truth table actually. If P is false, Q is true, then P implies Q is true. It can be true. P is false, Q is false, then P implies Q is true. So only false if Q is false. Only Q is false and P is true. So let's start with an example of this. I will explain this truth table with an example actually. I want to explain because a lot of people have confusion in this. So if both P and Q are true, then P implies Q is true. That is from the table. First, I will explain this first part. Okay. So suppose I will take two component statements. Suppose P n equal to 432 is divisible by 3. Okay. 432 is divisible by 3. And Q is a statement, the sum of the digits forming n is divisible by 3. So you can easily check P is true because 432 is divisible by 3, and Q also true because if the number is divisible by 3, the sum of the digits should be divisible by 3. So P and Q are both true. So how will you write P implies Q? If the number n is divisible by 3, then the sum of the digits forming n is divisible by 3. That's the statement, compound statement. And you have to write if then. Look at that. I have used if then. So that P implies Q is true. So it's clear case. No problem. So I will explain the next part. If P is true, Q is false, I will show P implies Q is false. So suppose P is a number, the number again the same statement as the previous one, the number n equal to 432 is divisible by 3, and Q is a statement, the sum of the digits forming n is not divisible by 3. So naturally it's very clear that P is true and Q is false. Okay, so P implies Q is false. So P doesn't imply Q. So this statement is false. P implies Q is false. So this is the example that explains this second thing. Now I will explain the third one, that is if P is false, Q is true. That gives you P implies Q is true. So let me go to the third part. Suppose P is a number, n equal to 431 is divisible by 3. The number n equal to 431 is divisible by 3. And Q is a statement, the sum of the digits forming n is not divisible by 3. So it's very clear that P is false because 431 is not divisible by 3 and Q is true. Yes, 431, if you take the sum, that is not divisible by 3. So P implies Q is true in this case. Okay. So that will give you the idea how will you do the truth table. Now I will explain the last part. If both P and Q are false, how will you get P implies Q is true? Let us use the statement. P is a statement. N equal to 431 is divisible by 3. Q is a statement. The sum of the digits forming N is divisible by 3. So P and Q are both false. Okay. So how will you write the statement? P implies Q. If the number N is divisible by 3, then the sum of the digits forming N is divisible by 3. So naturally, two false statements implication will give you true. So P implies Q is true. If the number is N is divisible by 3, but here the number is not divisible by 3, that is okay. This is false. And the sum of the digits is not divisible by 3, that is false. But what is the same implication? Implication is if the number N is divisible by 3, then the sum of the digits forming N is divisible by 3. So clearly P implies Q is true. So that is the explanation. So you have to remember only this one, that in the implication, that is P implies Q, this is false only if and only if P is true and Q is false, otherwise not. So similarly, you can write the converse of this. P implies Q, Q implies P is said to be the converse. So I will explain the converse now. Yeah, this is the truth table for converse. Implication. Converse is the implication. So P implies Q is the implication, then its converse is the implication. Q implies P. So you can easily construct the Q implies Q. So Q implies Q will be false if and only if P is false and Q is true. Okay? If and only if P is false and Q is true. This is the converse. And now I will explain contrapositive. P implies Q. If Rahul works hard, he comes first in exam. So its contrapositive will be negation Q implies negation P, which means if Rahul doesn't work, comes first, he doesn't work hard. So that is called the contrapositive. So contrapositive is nothing but the negation Q implies negation P. So this is the explanation. Truth table for contrapositive. You see, you can write the converse, you can write the truth table for the converse, you can write the truth table for the inverse and contrapositive. So again, you see the contrapositive is false if and only if P is true and Q is false in the table. So these are the important things you have to be very careful during the exams when you have a very compound. A lot of connectives are there, maybe 3 connectives are there. Now we are at the last part of our lecture today. It is biconditional or equivalence proposition. Biconditional. So if P and Q are two propositions, then the proposition if P then Q and if Q then P. That is P implies Q and Q implies P. Both side implication. So this is called biconditional proposition of P and Q. It is denoted by this both side implication. P implies Q and Q implies P. And it will read a P if and only if Q. If and only if. That is necessary and sufficient. Sometimes in mathematics we say it's what? Necessary and sufficient. If P is true, P implies Q, Q implies P. So that is the way. This is called biconditional or equivalence proposition. Suppose P is a statement, a number is divisible by 3, and Q is a statement, the sum of the digits forming the number is divisible by 3. So then P implies Q is a number is divisible by 3 if and only if the sum of the digits forming the number is divisible by 3. So look at that. A number is divisible by 3 if and only if. That is, if you break the statement, if the number is divisible by 3, the sum of the digits of the number is divisible by 3. And the converse is Q implies P. How will you write? If the sum of the digits is divisible by 3, then the number is divisible by 3. So that is why this is called biconditional implication. P implies Q and Q implies P, and it is read as P if and only if Q. So let us have the truth table for that. I think this is, oh, we have last, this is after this, we have a last slide. So P, first row says, if P is true, Q is true, P if and only if true. Second row says, if P is true, Q is false, P if and only if Q is false. Third row says, if P is false, Q is true, P if and only if false. And if P is false, Q is false, it is true. P if and only if Q true. So P, the biconditional statement is true if and only if both are true or both are false. That is very easy to, you can easily remember that this is true, it will take the truth value true or 1 if and only if both are true or both are false. Okay, this is also required in your table. Let's have the tautology. What is the difference? Now finally we are at the final table, tautology. So what is a tautology? Meaning a proposition formula or statement formula is called tautology if it assumes only the truth value t, only the truth value t. On all the corresponding cases, you have the last row of the connectives, you have only t. That is, in the truth table of the formula, every entry in the last column will be t. Then it is called a tautology. Otherwise, it is called contradiction. Contradiction means a proposition formula or statement formula is called contradiction if it assumes only the truth value f. So if all the entry in the last column will be t, it is called tautology. If all the entries of the last column is f, it is called contradiction. So let's have an example of tautology. You see, you have a complicated connectives. P implies Q or Q implies P. So I have to connect. So how will you connect? First you write P, first then Q. First you try to find out P implies Q and P implies Q is false if and only P is true and Q is false. Then you write the converse, that is Q implies P and Q implies P is false if and only if P is false, Q is true. Okay, and what is your P implies Q, or then you do the connective between P implies Q and Q implies Q, that is the last column, and you will see it will be true. All the entries in the last column is true. So this is a tautology. This is an example of a tautology. So please note down this one and how to do. You just break the compound statement into the several parts and do the table. It will be very easy. So you can explain the tautology with the truth table. It will be very easy to explain rather than using the different rules or laws. There is another one. You see, you have this compound statement. So you have P and Q. You can find out P and Q and P or Q. Then P and Q implies P or Q. You see, all the cases are T in the last entry. So this is a tautology. So this is how we have explained the several cases of implication operations. How will you do the operations in logic, and how will you handle the propositional calculus? So that's all for in my lecture. Thank you all of you.